Hello everyone, I'm Zhao from University of Michigan. Today I'm going to talk about our newly built modular centipedal robot and some preliminary results. So the motivation of our project is to ask this question: do more leg really helps leg locomotion? So except offering more backup legs for unexpected accidents that might cause robot or animal to lose their legs and potentially have more kinds of gaits, and it's easier to get a stable gait. So maybe there are more, but I will stop here. Otherwise, people will stop building bipedal robots. So another objective is to understand the relationship between simple and complex multi-legged system. In particular, how can we reduce a complex multi-legged system to a simple one? To answer this question without losing a lot of generality, we need a bunch of robots with different leg numbers, but with very similar structure as well as very similar gait. So then we can compare their performance. So to achieve this, we built this multi-pod robot, and multi-pod robot is a meter-sized centipedal robot that can have 4 to 12 legs with the same structure and can be tested with the same undulatory gaits. The fundamental base of this robot is the modular segments. Each modular segment has 3 motors for actuation and 2 leaf spring legs. To achieve undulatory joint gait, we drive individual modular segments in the same wave pattern but with different phases, and the phase offset between each segment is the same. Then we can have the same undulatory gait even we don't have the same number of legs. So the experiment we did is to run the multi-pod with different number of legs and compare the distance moved per cycle. And for each of the leg number, we run it with different phase offsets. And here are 4 examples of the 12-legged version running at 4 different kinds of phase offsets. And we use motion tracking cameras to get our experiment data. With this motion tracking data, we can have leg trajectories in the body frame. And then based on this, we can have individual phase for each leg. After that, we can have the global phase for the whole robot, which makes it possible for us to precisely find out each gait cycle. And then we can measure the distance moved per gait cycle. And here are some preliminary results. And from these 2 figures is about distance moved per cycle versus phase offset for different number of legs at 2 speeds. So some observations are here. You can see at a low speed, almost all the different number of legs is actually doing very similar thing. And at both speed, 8, 10, and 12-legged version move very similar. But when we increase the speed a little bit, the 6-legged version start to diverge more. And finally is about a surprising result. Half cycle offset taken by a lot of insects is not actually optimal for our hexapedal robot. And here you may ask, where is the 4-legged version? And that's the 4-legged version if we keep the same setting. It just fails. And to prevent failure, we need to reduce the roll amplitude from 25 degree to 15 degree. And we add the results from other leg numbers and do the compare, and we can see the distance per cycle are still quite close for 6 to 12-legged version, but the 4-legged version is different from others, and the profile is unimodal. So here is our preliminary observation. In the future, we will do more tests and try to build a model for the multi-pod robot. Then we can get a better understanding about the question we carried out at the very beginning. So because of the time, I will only mention 2 things here. The first thing is we definitely need to examine the dependence on the speed. We just fix the leg number, run with different phase offsets at different speed, trying to say whether our gait is more geometric or more dynamic. And the other thing I need to mention is about So actually, our robot has more potential because it's modularized. If we introduce pitch angle into our modular segments, we can have more gates. And here is an example of the interim gate. And it's weird, but it's a gate. Thank you, everyone. And any questions and suggestions?
This is interesting. So how many leg is enough? 8 to 10?
For currently we have 4 to 12.
4 to 12?
Yeah.
I mean, because you ask if it's more is better.
Yeah, we're asking whether more is better. So you're asking why we are picking 12 to be the maximum?
I'm asking how much is really the best.
For now, we cannot see because we didn't finish test all different speed. But for this for current speed, I think the 6 is the best one. Just based on the distance moving.
Remember, cycle. 6 is the best. All right. Okay, I will start from this side. Okay.
Alex, API. The Andy's paper, Andy Reno's paper on the collision and basically claims that more legs are better because you have a shorter, effectively a shorter, faster sequence of legs touching the ground. But that would only count in your case if multiple legs are not touching the ground in parallel. So if you basically have 12 legs, but out of those 12 legs, a third of them are touching the ground in parallel, you wouldn't make use of the principle what Andy's proposing to reduce collision.
I think because if we are using adulateral gates, the 4-leg touching is not have the same kind of effective stiffness. Because if you put the robot in the air, you can see the leg position like a wave. And when the leg is touching the ground, there may be 4 legs touching the ground, but they have different compression amount. And I agree with you. We can use this to be effective stiffness and maybe use sleep model to build a dynamic.
So you're actually not aiming for the aspect of reducing collision in the way Andy was describing it?
Now we are not reducing the collision because our leg is super light. All the mass is focused on our robot's body, so the collision itself will dissipate very quickly.
So then can you just state one more time, what exactly are you trying to? You're trying to change the effective stiffness, or?
That's not our goal. Our goal is trying to see whether, for example, 12-legged version can be represented by 2 sets of 6-legged version or 3 sets of the 4-legged version. So we want to see the relationship between a lower number leg multi-legged system versus a many-legged multi-legged system.
Yeah, just looking at it, doesn't look like collisions are important. And it looks like this is an example of one of these first-order dynamic systems. Did you check if you run the whole program twice as slow? Does it go basically exactly twice as slow?
You mean?
Is it that you're moving in a path and shape space here? It looks like.
Yeah.
And so and you're getting Lie groups and all that stuff, and you're just moving forwards. And if you do the same shape change, you get the same progress independent of speed.
Let's see this slide. So if the speed is super slow, not like this first figure, they are doing a similar things. And when we increase the frequency, it's changed a little bit, but we didn't to increase the speed more to check whether, like you said, if we double the speed of the system will just double or will have other dynamic effect. And I will just quickly show a very interesting observation we had, but since it's only one trial experiment, I'm not sure, so it's not convincing, but it may give us some sense about what happened later. So here is when we really increase the robot's speed to its limit, and we can see this kind of very special drop for the 6-leg version, and for the 8-leg version, it's increased a little bit. But don't trust this data, it's just only once. I need to run every experiment several times to make sure it's true. So.
Okay. Question there.
Yeah, well, Bled from Calgary. So often if we're comparing things in biology, we normalize to some sort of measure of size. And here it looks like you're not doing that. So I have two questions. First is, why not? And then the second question is, you did normalize to size. It looks like smaller is better because you double the size and you're basically not compromising distance traveled at all.
Yeah,
so if you're normalizing to length, it looks like per body length, the smaller is doing better. And so can you comment on, does that mean anything for what you care about?
Yeah, that's a good question. And we all know biologically people will use the criterion to describe the speed. And this criterion is speed per body length. Because I think using this criterion is because most of the animals we study is because their leg length is sometimes proportional to their body length. So if you have a very large body and a very long leg, then this kind of criteria does make sense. But in our case, when the body increases, the length of each leg does not change at all. So I don't think this kind of criteria can fully represent whether our robot is doing a good job or not.
Another way of thinking of that, though, is thinking of performance divided by cost. And you could think of the length as an additional investment in your robot. So in essence, you're not thinking as much for adding more legs. It's just something different.
Yeah. So we definitely in the future will test the energy cost. Because for now we are using the criteria of distance per cycle, but in the future maybe we'll do energy per cycle, do the test and see.
Okay. Can take one more question, Peter.
What happens if you pull the legs off, one by one?
Yeah, that's the promising project, and we do have some failure doing experiments, and some of the leg just fails and is dragged on the ground. That still can achieve almost 90% of the moving distance. And as we mentioned at the very beginning, having a lot, that's also the biggest advantage of having more legs, because you can always afford breaking one of them. So.
Great.
Thank you.
Thank